Okay, so while we wait for a few more minutes for people to come in, I will give a brief introduction of our speaker today. Welcome to the Photonic Innovation Center, the OSA and SPIE student chapter sponsored seminar. Today, the title of the seminar is Microcombs Unifying the Optoelectronic Spectrum at the Chip Scale. And we're very delighted to have Professor Kerry Vahala here today to give this talk. Kerry Vahala is the Jenkins Professor and Professor of Applied Physics at Caltech. And he's best known for his research in ultra-low loss, which are also known as ultra-high Q, optical microresonators and their applications. So these resonators, these ultra-high Q resonators used to be very large, or they were formed by bulk optics. But over the years, his group has miniaturized these devices so that they are in a chip scale form factor. And that opened up many new areas of physics and applications because the circulating intensities in the chip scale microresonators, these ultra high Q resonators, were much higher than in the free space ones. So some applications that these microresonators have found include laser sources, optical frequency references, microwave sources, quantum optics. And prior to his ultra high Q resonator work, he was very well known for his work on quantum well lasers and their noise and dynamic properties. He has been recognized with numerous awards, including the IEEE Sarnoff Award, the OSA Paul Foreman Team Engineering Excellence Award for a 2-photon optical clock, the NASA Achievement Award for the application of frequency combs to the exoplanet search, the Alexander von Humboldt Award. He's a fellow of the IEEE and the OSA, and last year in 2020, he was elected into the National Academy of Engineering. And personally, I've known Kerry for nearly 20 years. He was my professor in a quantum electronics course at Caltech back in 2002. He was an excellent teacher. His quantum electronics class was very technical, in fact, and really prepared all of us to enter the field of photonics and nonlinear optics and laser physics. And for me personally, it's also been very amazing to see how this field of high Q resonators really blossomed during my time as a PhD researcher to now as sort of a professional researcher. So from the early 2000s, so when I was a PhD student, his group was working on these very, very exquisite microsphere resonators and the erbium lasers, microsphere lasers that came out of that, and then that evolved into toroids and then wedges, and now the various form factors that are now even fabricated with lithography processes. So they can be made on silicon and at wafer scale. So again, I'm just so happy that Kerry's here again today. He last visited Toronto almost 10 years ago. With that, I'm sure he'll tell us more about his new research. Lots has changed in the past decade. So I pass the floor to you, Kerry.
Yeah, thank you very much, Joyce. And yeah, for that great introduction overview. And I'm really happy to be back, even virtually, okay, at the University of Toronto. It's been just about 10 years, and good timing. It gives me a chance, as you were just sort of mentioning, to kind of bring everyone up to date on what's been happening with optical microcavities. And so, as you said, there's a lot that's been going on. There's many different application areas that are being studied. The one I'm going to focus on today is one that has really heated up in the last 5 years. And this is the subject of frequency microcombs that belong to a broader class of devices that are frequency combs, which I'll be telling you a little bit about. The overall theme today, though, the message I want to leave you with, and I'll kind of start with that message, explain what I mean by this, and then I'll return to it at the end of the talk, is the idea of spectral unification and unification of the optoelectronic spectrum, and how microcombs are really transitioning us, to this kind of capability, new capability, but at the chip scale. And at the very end of the talk, I'll kind of discuss how this, might unfold and impact technology in the coming decades. So, so let's start and begin by first giving you an idea of what I mean by spectral unification through several well-known examples that we, perhaps we don't think of it this way, but these are, technologies we run across in the lab, everyday life that actually rely upon spectral unification at audio, radio, and microwave rates. And then after, kind of laying that definition, I will then, discuss the frequency comb technology. And it's, quite a remarkable, feat that it performs. It is actually spectrally unified photonics and electronics. I'll explain how it does that and, some of the ways that frequency combs have been applied. And then that'll lead me into the main part of the talk where I want to, discuss these little, miniature frequency combs that are now, we can make them readily on a chip. What's going to happen as a result of that? What are the physical principles at work in these little combs? And then I'll finish up by talking about the kind of recent progress on integration. There's a tremendous amount of work in this area now. It's really taken off. A lot of groups and a lot of eyes, so to speak, are working the problem. So it's moving fast, a very competitive field. And so I'll show you some of these latest efforts on integration, system demonstrations, and then how this is going to play out near term, long term in the future. So that's kind of the roadmap for today. All right, so first of all, what do I mean by spectral unification? And so I'm picking two examples that have a parallel in the world of frequency combs. And so the first is something we're all, we use these all the time. These are frequency synthesizers. They're lab instruments that, purchased from, Keysight, Rody Schwartz, there's a lot of different manufacturers. And we don't really even think about them, as that remarkable anymore. But, they really are quite a remarkable tool. And if you've ever looked at the diagram for how a frequency synthesizer operates, I'm showing you, one version. There's several different versions of this, but this is a version that is basically illustrating, the key parts that I want to emphasize. And so there's two oscillators, all right? There's a reference oscillator you see there. If you can see my cursor. This is a low frequency oscillator, typically low frequency because the best reference oscillators we have now that are low cost are quartz oscillators. They've been, refined and perfected over many, many decades. And so these operate, typically, tens of megahertz. But to generate a wide range of frequencies out to the microwave, what happens is that in a synthesizer, you pair together this very nice reference with a very high frequency oscillator. So this is the voltage controlled oscillator you see over here. This could be like a YIG oscillator. So if you purchased a microwave synthesizer, then what you'd find typically inside is you'd have one of these little quartz devices and you'd have a YIG device, and they work together. They coherently are coupled together through a lot of other electronics, and that's what I'm showing here. There are dividers. There's typically also multipliers, but in this scheme there's only dividers. And the idea is that we are able to type in to some level of precision, some large number of significant figures, the frequency of a sine wave that should be generated by the synthesizer. And we push the button, and then the instrument produces the sine wave frequency that we like. And in this case, this is showing these fractional or these ratios that can be produced as multiples of the reference here up to the VCO frequency. And I'm showing just a few examples of these sine waves. So this is a very familiar kind of a tool. And I'll come back to this in a moment in the optical context, but just to kind of hint at what the frequency comb is going to do. The frequency comb is basically playing the role of all of this electronics in between. And so it's really going to do this. And so we're going to come back again to these two oscillators over here. And, but the comb will be doing all the electronics. All right, so this is one example of unification, one familiar example, where we're going from a low frequency to a high frequency. Let's look at another. And so this is another very familiar one, maybe less familiar now because, wristwatches perhaps have, somewhat gone away, but, we rely upon, phones, smartphones now for timekeeping. But, not that long ago, this was a kind of a very, very inexpensive little quartz wristwatch, okay, that you could buy. This one I had and disassembled it quite a long time ago. And so what I want to do is I want to illustrate or use it to illustrate how modern clocks operate. And so all clocks, which represent now kind of the reverse direction from what I just described in the synthesizer. So in the clock, we'll start with a high frequency, and then we will connect the high frequency down to a low frequency. In fact, the low frequency will be the second. All right, so we'll want to create a, a tick, okay, on a clock. And so in the wristwatch, the way this works is that, I mean, here's the battery, here's the liquid crystal display. There's some electronics hidden behind the LCD that I'll come back to in a moment, and a little cylinder. And if you open the cylinder up very carefully, here's the, the quartz tuning fork, okay, that, many years ago when, ads used to run about, quartz precision, in wristwatches. This was the little tuning fork that, was providing the accuracy and precision for the watch. And so the way this works, and again, this is how all clocks, even the atomic clock, the cesium time standard clock that is used, as the world time standard, they all work this way, that there's a reference, a high frequency reference. In this case, not that high a frequency. It's only, it's 2 to the 15 hertz, 2 to the 15th hertz. And so it's a little higher than audio. But the electronics divides. And so the electronic circuit, series of counters will divide by 2, 15 times. And then the output, okay, will produce a second. And the second, the accuracy of the second depends on actually the ability to really do this, to machine these little quartz tuning forks so that they vibrate, all right, at 32,768 hertz. And then you can also see that, the reliability or the accuracy of your wristwatch depends on, for example, like how temperature affects the tuning fork. And here you kind of rely upon body temperature, all right, to actually sort of maintain a kind of a constant environmental bath that maintains sort of the average frequency of the tuning fork. But if you're skiing or if you're at the beach, okay, obviously there's going to be a change in temperature, and so this is what causes some drift in your wristwatch. So better clocks rely upon really having better references, and better references run at typically we've learned over many decades, better references are running at higher frequencies and higher Qs. Okay, so that's kind of what I mean. That explains the idea of spectral unification in terms of 2 familiar examples, one going from low frequency to high frequency, the other going from high frequency to low frequency. So now let's turn the attention to unification, but on a much, kind of grander scale, all right, between optical frequencies and electronics. And again, this is what frequency combs really do. So I'll come back to that in just a few charts. But what I want to make clear, okay, is, what am I not talking about, okay? Because, I mean, there's many different ways, many different, technologies that we have available to coherently couple light with electronics. And so we are able to detect light waves that are modulated and turn those into electrical signals. We are able to, take an electrical signal, modulate a light wave, for example. So there is a back and forth, a very, very well-defined technology space that allows us to go back and forth and to connect in some sense, electronic signals and optical signals. But that is not what I'm talking about here. What I'm talking about is really this idea of real coherent connection, right? So the ability to divide optical signals, okay, at hundreds of terahertz all the way down to radio frequency rates, and then ultimately even to be interested in producing a time standard for the second. Or the reverse, multiply, electrical rates up to optical rates. And it's pretty obvious that this is a difficult thing to do, and it was until very recently, extremely difficult to do. And the reason is just a huge gap in frequency between electronics and optics. Electronics simply cannot, operate at optical rates, where you're looking at, hundreds of terahertz, okay, of rate. And so that's been, that's an obvious, gigantic hurdle, okay, so to speak, in sort of having this sort of unification that we take for granted at audio, radio, and microwave rates. But what's kind of curious, and this just shows you, human curiosity, very, very soon, okay, after the invention of the laser, and so in the 60s, the laser, in some sense, you can think of it intuitively as the optical, equivalent or optical manifestation of radio and microwave oscillators. And so it's producing sine waves, okay, and classical, we can think of them as semi-classical waves, but they're these nice electric field sine waves at high rates. And so it was natural, just because by the 60s, synthesis had already appeared. In fact, the first commercial radio frequency synthesizers were beginning to appear from companies like Hewlett-Packard. And so it started, scientists at that time thinking about, could you do the same thing with light fields? And would it be possible to actually, create a coherent link between a radio frequency system and an optical laser? Or if you could do that, even maybe, connect it up to an atom. And if you could do that, could you go in the other direction? So there were all kinds of, interesting ideas that popped up as a result of having now an optical oscillator, okay, that would be the analog of radio oscillators. And this led, okay, to a 4-decade-long, pursuit that was ultimately successful at several laboratories around the world to create what are called frequency chains. And these are now really, these are devices from, you can look at them, a bygone era, okay? So they were highly complicated, very impractical, but kind of in some ways a brilliant idea. I'm showing you one of them that was successful here on the right. This was demonstrated at the National Bureau of Standards in Boulder, Colorado. That's now NIST, okay, the National Institute of Standards and Technology. There were other chains, okay, that were developed. Some of the most advanced ones were in Germany, actually, in the late 90s, and they succeeded in actually making this coherent link. And so as a result, a couple of very significant scientific experiments were conducted. And so there was a period of time, for example, when the speed of light was actually sort of verified to a higher level of precision by actually measuring very precisely the frequency of krypton and then coupling that with precise measurement of the wavelength of krypton. And that measurement of the speed of light actually, later gave way to actually the definition of the speed of light. Okay, so speed of light is now defined, and the second is defined, and then that combination, the second is the result of a cesium time standard, and that combination allows us to define the meter. So there were a whole lot of interesting little chain reactions, okay, that came about that are profound. I mean, they actually have impacted the way we think, we do science today, some of our standards, because of the development of these frequency chains. But again, they were really, you can tell they occupied multiple laboratory bays, and you really couldn't envision this ever being, widely used, okay, widespread. But along with the chain work, there were also researchers that were trying to understand how could you miniaturize chains. And miniaturization at this level is not what I'm going to talk about in a moment, where we're going to a chip. This is miniaturization now going from something that's the size of a small building, okay, down to hopefully something that might be a rack mount instrument. And there were a couple of really important developments through the 90s that gave way, okay, to a really profound invention, okay, 20 years ago, and that was the frequency comb. And the frequency comb really was invented and perfected at 2 labs. Okay, one was MPQ in Garching, Germany, and this was Ted Hensch's group, and the other was Jan Hall's group in Boulder, Colorado. And there's a series of papers that appeared just around 1999, 2000, 2001 that completely set the stage and defined, okay, this subject that still is having amazing impact, okay, all across photonics. I think, in my mind, this is probably the most important optical invention in the last 25 years. I mean, if you really dig into what it's done, and I hope that maybe just from what the little brief description I'll give you in a moment, maybe you'll begin to see why I can say that. But what a comb does is it gives us this bidirectional connection that I mentioned earlier. It's this unification, but now on a much bigger landscape. We're connecting together optical frequencies at hundreds, of terahertz with electronic frequencies, and we can go back and forth, and we can do this very conveniently. And these are now commercial devices that are about the size of a shoebox, and so we've gone from lab bays down to a shoebox. And how have we done that? Well, the other kind of remarkable part of the story is that it uses a very kind of a well-established tool in optics, and that is the mode lock laser that was really the idea of mode locking came about in the 60s. And so I'm showing a, kind of an animation that I borrowed from one of my friends, Scott Diddams, of a titanium sapphire mode lock laser. And so there's many longitudinal modes in this cavity. They are, phase locked together to produce these ultra short pulses. Now, it's kind of hard to imagine how this would, allow us to, make this bidirectional link. So let me just kind of go through, kind of real quick hand wavy explanation. So the output, if we look at it in the optical spectrum, so the Fourier space of these little pulses, they're periodic pulses, and so there's a set of lines, okay, that correspond to the modes of this cavity. And what is done, okay, the core, the key idea that takes a conventional mode lock laser and turns it into a modern frequency comb is a process called self-referencing. And self-referencing is really the core of the Nobel Prize, or half the Nobel Prize. And here's the idea, is that each of these comb lines can be given a label, F sub n, where n is the index, an integer index. The repetition rate, that's something we can easily measure. Put a photodetector at the eye, it produces a periodic current. But it turns out that in order to measure the frequencies of the comb, and that's what we really want to do, this is what's called self-referencing, we need one other number. We need this F0 number, and this F0 number, you can think of it as like a fictitious comb line that would be the n equals 0 comb line. There's no energy down there, but pretend that it's there, okay, anyway. So how do you measure that? And how do you turn it into an electrical current? Well, there's a couple of steps involved. The first step is broaden the spectrum of the pulses. So the pulses are broadened out to over an octave, right? So this is supposed to be an octave, right here, my little hand-drawn spectrum. Take a few of the comb lines at the low frequency end here and double them using a nonlinear crystal. Compare those now, their replicas to these high frequency lines that are out here at the other end of the comb spectrum after it's been doubled. And the beat frequency you can show really quickly, just a line of algebra gives you F0. So F0, through this little process of self-referencing, can be measured, turned into an electrical current, and then you can use that to servo control the cavity so that now F rep and F0 can be stabilized to like a radio frequency source, like a piece of quartz, for example, or even better, a maser. And then all of the lines of the comb are now established. And literally, we literally know where they are modulo, okay, the line spacing of the comb. So with a little bit of help from a gradient monochrometer or an atomic line, you will then be able to know where a given comb frequency is, all right, to an incredible and unprecedented level of precision. And so just this little idea alone actually launched a whole, new, category of high precision spectroscopy, even new techniques for doing spectroscopy. But this is only one part of the story, right? So this is kind of a picture that shows you, what else can be done with a comb. And so here I'm showing a Fabry-Perot cavity instead of a TISAF cavity. And these are supposed to be the modes, the longitudinal modes. And so here you can see the little equation for the nth frequency. We're envisioning that these modes are locked and they're producing these little pulses that are emitted out this mirror. So whenever the repetition rate would be the period of these pulses are not shown as being very narrow, but they in principle would be very narrow. They'd be femtosecond timescale pulses. All right, so the mode of operation that I just described, right? So the self-reference mode, where you input radio frequency signals, stabilize F rep, stabilize F0. That is represented, okay, down here through this kind of mechanical analogy of what the comb is doing. And so here is the input radio frequency signal. It drives this little microwave gear. And what literally happens, what the comb is doing is it's transferring coherently, in a completely coherent sense, okay, the radio frequency control all the way up simultaneously to all of these lines. And there's about there can be hundreds of thousands of these lines, a million of these lines, depending upon the comb repetition rate, that are spanning this, this octave. And so this is what we call synthesis. Okay, so this is this mode 1 below. But as I said, there's two other modes of operation, and this is again why this device is had such huge impact. You can go the other way. All right, it's bidirectional. So rather than specifying the microwave frequency, specify one of the comb lines. And so how do you do that? Well, this comb line could be locked to a very stable reference cavity, or even better, it could be stabilized to a very long-lived dipole transition in a cold atom or in a lattice of atoms, a lattice of cold atoms. And if you do that, then what happens is that now that amazing optical stability is coherently transferred down to an electrical signal that can be detected. This is just the pulse rate, okay, out of the comb. Detect the pulse rate from the comb, divide that down further using electronics. You now have the basis for now what are the most accurate clocks, okay, known. These are 100 times more accurate than the current cesium time standard, and they will become the future time standard. All right, and then finally, the third mode of operation, this is one that really has a lot of scientific importance, is that the whole system, it can be configured so that it's possible to transfer coherence between, you know, two of these lines that extend over an octave. And so this has become really interesting in comparing, you know, with incredibly high accuracy, transitions in different atoms or the accuracy of different styles of optical clocks. And so there's, again, kind of these three different modes of operation. Okay, so coming back again to the big theme, all right, so we have the synthesis, which I originally described as, you know, quartz to radio, quartz to microwave, and now the synthesis is occurring, okay, radio to optical. And I'm just showing two comb teeth here. And then the other direction, okay, is division, and this would be the clock, okay, style. So this is formally equivalent to the wristwatch clock. But now starting with, for example, a cold atom or a cold atomic lattice, divide these transitions down. And you have to remember what really is going on here is that the cycles of oscillation of the atomic dipole are literally being counted, and they're being counted and divided down to produce, you know, electrical signals that then establish a new definition of the standard. And by the way, this is not only the basis for the best clocks, but this is a kind of important, I would say, victory, okay, for photonics, that, you know, the very, very, you know, best microwave and radio frequency oscillators that are now known are basically, you know, they use this principle of what's called optical frequency division. They're vastly more stable, okay, than kind of the previous gold standard, okay, which was based on sapphire. So in the future, you know, it's really clear, I think, maybe after the talk today, that, you know, on some time scale, we will have, you know, very, very stable radio, microwave, electrical oscillators, but the core of those devices will be optical. And so that's, you know, one other impact of all of this. Okay, all right, so now with that, let's kind of move on and look at miniaturization. And so there's several steps that I want to go through. First of all, let's talk about the physics and what we need to do, and then we'll look at integration. All right, so come back to this basic picture. So this is the last 20 years of frequency comb technology, tabletop combs, and so, you know, I've kind of gone through these steps a little bit, but here's the mode locking process, which today, actually in a commercial device, is most often done with a mode locked fiber laser. All right, so really, you know, powerful technology in its own right. Here's a nonlinear optical fiber that's used to broaden this. All right, so these are special fibers that really came into existence around the year 2000, same year as the invention of the frequency comb. And then we've got some nonlinear optics needed to actually self-reference the device. All right, so these are key things we need to do and transfer over to a chip to create a comb. All right, so today I'm going to spend really all the time, okay, talking about the first part of this, the how we create very stable mode-locked, you know, systems, okay, on a chip that are stable enough that they have now moved very rapidly into full, you know, chip-based comb systems. But, you know, if we had more time, all right, I could tell you about, you know, all of the other pieces, the ingredients here, because they're interesting in their own right. There just isn't enough time to talk about them today. So the octave span generation, amazingly, the octave span generation, we don't use optical fiber. The octave span is actually done inside the little resonator that's going to generate the frequency comb. And so we get mode locking octave span, all right out of the little device. A couple of other features, detectable repetition rates, the harmonic generation, the detectors, the amplifiers, not surprisingly, those are already available on chip. But the point is, and I'll show you this a little later with some you know, actual demonstrations, you know, everything is now on a chip, and now it's not a matter of, you know, getting it onto a chip, it's a matter of just continuing to refine, okay, the integration, and that's moving incredibly quickly. All right, so let's talk about the physics, all right? Just what goes into the mode locking process. That's what I want to really turn attention to in the next few charts. So Joyce kind of, talked about this a little bit in the introduction, but the devices, with exception of one particular device that are used now for these microcombs, are whispering gallery resonators. So very, very high Q whispering gallery resonators. And there's a whole range of, it's kind of an interesting subject in its own right, just kind of fascinating to look at all the different ways that groups are manufacturing and fabricating whispering gallery resonators. Some of them are discrete, like over here, this is sort of semi-discrete. Some of them are fully integrated. There's versions I'll show you later that are very new, that they're completely fabricated now on CMOS lines, okay, literally CMOS lines. And we're now, using those. But they all have in common that light is guided in a little ring orbit, and so I'm kind of showing that down here. Here's the little ring orbit in this little silica microtoroid. There's a round trip condition. It's necessary to pack in an integer number of wavelengths and material. That sets up, the resonant frequency spectrum, and so in the end, each of these little whispering gallery resonators has a round trip condition, and they support approximately equally spaced set of modes. There's dispersion in there, so the modes are not perfectly equally spaced, but they're, you can think of them as kind of like a comb spectrum. All right, so now it's easy to make these devices. I mean, it really is. If you have access to a fabrication facility, you can readily make some little whispering gallery resonators on a chip. But the next step is harder. And 20 years ago, it was super hard. 10 years ago, it was hard. Today, it's gotten a lot easier. There's a lot of tricks, okay, that have been developed to do this. But the Q has to be high. And the Q has to be high because we want to have strong resonant enhancement of coupled light into a small mode volume. And as Joyce was mentioning, if you do this, it's kind of remarkable what happens, but the circulating intensity will scale like Q over V. And so if we look at that little toroid, for example, then, not a lot of power that's readily available from, telecommunications lasers, 3.5 lasers, will generate huge circulating intensities. Even the absolute powers are large, right? So the power in a microtoroid like this that has a Q in the hundreds of million, if you're launching tens of milliwatts in, you can actually get to kilowatts, okay, of circulating power, continuous power. And so all of a sudden, nonlinear optical effects that would typically require, a lot of, tabletop laser power, okay, to access are accessible using, little tiny, chip-based lasers. And so this is really, part of the story here. And if I pull out one of the nonlinearities, okay, in fact, this is the key nonlinearity that is used to make these new microcombs, the Kerr nonlinearity. There's a couple of aspects of the Kerr nonlinearity I want to go through in a little detail here, the physics, that allow us to mode lock and leveraging this high circulating intensity. And so this is one part of it. And the Kerr effect, again, it's a third order nonlinearity. And so one way you can think about it is that it's taking pump light, that will provide pump photons, two pump photons scatter elastically through this nonlinearity, exchange energy. There's a signal and idler, okay, that are produced as a result of this. In the cavity, that basic interaction leads to gain. Okay, so it's gain very much like what we're used to thinking about in a stimulated, emission sense or a two-level system. But this is coherent gain. This is a gain that results from a parametric process, not a stimulated process. But it still leads to threshold. So it's a thresholding process, and it's a regenerative oscillator. But it's a little different from what we're normally used to thinking of in lasers. You have this pair. Okay, so we have a pair, a signal-idler pair, and the pair begin to oscillate as a result of pumping. And importantly, the signal-idler pair are about equidistant in frequency from the pump as a result of the fact that the scattering process is elastic. All right? And so now coming back to the threshold, the turn-on power, okay, Q helps us a lot here. So high Q, actually the Q enters inverse quadratically to the threshold, the turn-on power for this little oscillator that we have. And you can see the numbers are really low. So this was data taken quite a long time ago in a microtoroid but it's pretty typical, okay, even today, of the turn-on power for, to achieve parametric gain and oscillation. Now, why is parametric gain and oscillation important in microcombs? Well, it turns out this is the process that we use to actually drive the comb. And in fact, the combs turn on, okay, at this threshold power. And so you want to be paying close attention to Q because Q is going to make it easier, okay, to turn on these combs. Now, how do the combs actually form? Well, this is an interesting story as well. So here's the parametric oscillator. You'll see these extra little lines that are appearing over here. Well, these are the results of mixing, third order mixing that's now occurring between these three lines, okay, once they form. And we started to see this effect, okay, right at the same time as, the parametric oscillation. And in fact, if you pumped it hard, okay, you could see a whole set of lines through a process called cascaded four-wave mixing. Now, the person that connected the dots, okay, on this and actually sort of coined the term microcomb for this was Tobias Kippenberg. So a couple of years after this, he was involved in this early parametric oscillation work, and then later tested out in a very broad cascaded comb like this and showed that you could make it operate and function, okay, as a kind of a comb on a chip. And so this created a tremendous amount of interest, obviously, because if you could put comb technology, which by 2007 was already becoming pretty well developed, if you could put it on a chip, that would be a very big thing. And so there were a lot of groups, okay, that jumped in and started looking at these devices. It became clear pretty soon that there was some missing ingredient, okay, that we didn't have here. And in fact, sometimes the combs would come up and they would be, coherent, and sometimes they would come up and they would be noisy. And the missing ingredient kind of fell into place a number of years later, and this was pulse formation. So what we think of as sort of true mode locking, in the sense of when I think of mode locking, or probably when most of us think of mode locking and a laser, we think of formation of short pulses. And in other words, phase aligning all the modes of the cavity so that we can actually produce a short femtosecond timescale pulse. And that, really is an essential ingredient. It was brought in, okay, in 2014, and it really was it was a critical turning point in the subject. And I think, a lot of the key ideas have come into place since 2014. And so I'm showing you a couple of the early reports here, 2014, 2015, 2016. Some of the key papers were beginning to actually do true mode locking, okay, based on, this Kerr, okay, nonlinearity. And these are representative spectra. They're optical spectra. In some cases, you can see the comb lines. Other cases, the comb lines are too close together to resolve. But the kind of comb spectrum that's produced here has the shape of a hyperbolic even squared in the spectrum, and produces a nice little pulse. All right, so what is the pulse itself? Well, again, continuing kind of the physics here for just a few charts. The pulse is a soliton, as it turns out. And the idea for this new type of coherently pumped soliton was actually proposed theoretically a long time ago. There was a paper in the early 90s, okay, that actually, indicated that you could do this. In fact, by the early 90s, we were already studying, fiber solitons. That was a super hot subject. Okay, in the 90s, it remains a very hot subject today, but in the early 90s, it was still even thought of as a possible way to send information, okay, over long distances. But those types of solitons used, the Kerr nonlinearity to form the soliton, but they did not actually come with their own kind of gain. And so that was the difference here, this new kind of coherent pumped soliton. It took many years, okay, before actually those solitons were seen. It was some 17 years later before they were first observed, and this was in optical fiber. And then it was 4 years after that until they transitioned into the microcavities and gave us really the modern microcomb, okay, soliton microcomb. And I want to just tell you a little bit about, again, a little more physics. This is actually the equation of motion, right, for these new solitons. And so it's called the Lujano-Lefebvre equation. The part that I'm outlining here is really a part that if you study solitons in optical fiber, you're probably very familiar with it. It's a kind of a nonlinear Schrodinger type equation. There's a second order dispersion term here. We could actually add higher order dispersion terms. Theta is the coordinate of the soliton as it's going around the cavity in this case. Here's the Kerr effect. And the Kerr effect is actually compensating the dispersion, right? So that's one of its jobs. But the new terms are over here. Okay, so here's a loss term. This is something that's a little bit new. And that loss term is coming from, you know, the cavity losses, absorption, scattering, the intentional coupling of the soliton out the cavity. And because of this coherent amplification that we have, that loss is actually compensated. So the Kerr effect is compensating loss, compensating dispersion. And so this is a mode-locked, you know, parametric oscillator, all right, in the end. It's, you know, quite a different animal, okay, than the, you know, the predecessors, which were the soliton, you know, mode-locking devices that relied upon, for example, erbium fiber, okay, amplifiers to provide their gain. These come with their own built-in gain. Here's the pumping term that's giving us that gain. This is the field, the input field, and that's also going to be one of the comb lines in the end because this is a coherent process. And I want to tell you a little bit about how you turn on the laser and how you turn on the solitons. And so this is detuning frequency here, okay, that this delta omega, and omega 0 is the frequency of one of the whispering gallery modes that we're going to pump. This is the pump frequency of the field, okay, that's doing the pumping. And to kind of understand how we get the solitons going, I'm going to again look at the resonant buildup. And so here's intracavity power. Here's the detuning frequency, delta omega. When delta omega is equal to 0, that means omega p is equal to 0. We're right on resonance. So if the Kerr effect were 0 or if the cavity Q were low, all that we would see is this gray curve and resonance would go up and down. But as the Q increases and the Kerr effect is enhanced, this will pitch over. And then what you'll see here is that there's going to be a region of bistability. And I've colored in this region in the back, and this is where the solitons will form. And so in the laboratory, what happens is that if the pumping laser is scanned, so if we scan omega p, and we have to scan it from blue to red, all right, this has to be positive because of the sign of the Kerr nonlinearity coefficient G. But if we do that, we would start to ride up that bistability curve. At some point, the laser would drop down. There would appear this little step, and this is data over here where we're actually doing that. This is a time scan, but you've got to think that the laser is actually scanning from blue to red. So it rides up the bistability curve, it drops down, and then there's a step. And the step is actually the manifestation of a soliton. And so just to show you how that works, this is data that is taken using a very, very high-speed sampling system, coherent sampling system. And we're going to observe, in this case, solitons, these little currently pumped solitons form inside this little wedge resonator. This is a silica resonator. And this little ring, I want you to watch this ring. And the ring is going to be showing us the data in which, as we scan the pump, okay, we're going to go from red or from blue to red, but now we're monitoring actually the transmitted power, right? So this is kind of the reverse of what I had on the previous chart. This is the transmitted power as we come into resonance past the whispering gallery resonator. And so I'm going to turn on the pump, we'll begin to scan the pump. As we come into resonance, we're now seeing all of this, what I call noisy comb. I mentioned this noisy comb before. This is the cascaded forward mixing. And then as we eventually get to over here, we'll enter the bistability regime. And now you see 4 solitons, but we continue to scan, and now we'll see 3, 2, 1, 0. All right, and so in this case, you can only see that we can put 1 soliton in, but we can load this cavity up with multiple solitons if we choose. You also can see that it's pretty obvious that to make a practical device, it's necessary to actually put the laser frequency, the pumping frequency, onto one of these steps and to hold it there, and to hold it very stably. And 5 years ago, this was quite challenging to do, but within a few years, there were several techniques developed that involved, as you can imagine, elaborate servo controlling mechanisms that would put the pump where we want it to be and hold the pump at that position. So it became possible to do this conveniently in the laboratory. But what I'll show you in just a moment is that there's now very new techniques that have been just invented in the last 2 years that enable us to do this automatically. So it's just like turning on a light switch. We don't have to worry about anything in terms of finding the step, holding the step. It all happens without any kind of servo control. Coming back to the Lugiato-Lefebvre equation for just a moment, this turns out to be a really powerful numerical simulation tool, and I'll just kind of show you that here. This is a numerical simulation of a single soliton. Here's the comb spectrum, and you can see it forming as a hyperbolic secant squared, and this is actually following a little soliton around in the cavity. And I'll run that one more time. So here's the spectrum, and we're in the frame of reference of the soliton, and you can see that little soliton form. As we go deeper into the step, the soliton actually acquires more and more power. So this is how you regulate the power of the soliton and also the comb bandwidth. It's through this detuning. All right, so that's the physics, and so now let's look at integration. All right, so first of all, I'll show you some of the system demonstrations that have been realized that give you an idea of the level of integration that's now possible. But I want to come back to this business of actually how to turn on, trigger, and hold these solitons without having to think about it, so to speak, without any servo control. And this is really quite a new result. This is results from a collaboration between the Bowers group at UCSB, Kippenberg group at EPFL, and my own group. And I'm showing some of the results here. There's two main things I'd like to point out. One is that this is a fully packaged microcomb system. It's not self-reference, but it's a complete system in the sense that it has its own pump laser, 3.5 pump laser. It has a microwave rate comb on board. They're all packaged together. They now are hybridly integrated. This is all done hybridly integrated. When this was supported, they were just sort of positioned next to each other. There's no isolator on board here. We actually do not have an isolator, so that's kind of a nice thing, and I'll explain why that is in just a moment. But it's all pigtailed, and so essentially it's a fully functional little microcomb. Now, the other key point is that, as I mentioned, there's no isolator between, this is the comb resonator and this is the pump laser. So normally in the early days, just over 2 years ago, so 6 years ago, we'd isolate between these two. But we found actually it's better not to isolate. And in fact, actually the presence of the Kerr effect feeding back into the cavity does something very interesting. And so coming back to this bistability curve, you can see down here, previously the way I set up the problem, when I showed you the movie before, this little dashed line that you see here was vertical. I was literally scanning the detuning, and as we moved into the bistability regime, we had an ambiguity. There would be a problem. If I tried to trigger the soliton, I might get a soliton, I might not get a soliton. The laser wouldn't know where to be. Actually now, as a result of the presence of the Kerr effect coupled with the cavity, that line, which you can almost think of as kind of like a load line, is now pitched to the side. And actually there's only one operating point. And that in combination with the locking that occurs upon feedback means that once we turn on the pump laser, the whole system snaps into alignment and immediately begins to produce solitons. And so this shows you that happening over here. Here we're just turning on the laser. This is the soliton power. This was a K-band soliton. You can see the frequency that we're measuring here. This is doing it repeatedly. We're turning it on, off, on, off. There's no control here. In fact, actually the temperature even drifts a little bit. And so you don't need much temperature control. And so this is a brand new thing. It's tremendously simplified, actually, the operation, and the integration of these little microcombs. To do style of soliton, if you work with solitons, I'm sure you're familiar with these. These are called dark solitons. These are kind of like the reverse, of or inverse of a bright soliton. Bright solitons need anomalous dispersion to form. Dark solitons can be formed with normal dispersion. And they have a funny looking spectrum. They're not hyperbolic secant. They kind of look like this. And you can think of them more as like square waves. And they have some really intriguing and important properties. They're much more power efficient. And so a lot of the work that we're doing right now is actually focused on these dark solitons. But this is just showing you some of the comb or the dispersion spectra, for the mode family we're using to form the solitons. Now, the other thing I wanted to mention, and this is also really new. This is, again, work between John Bauer's group and my group. These are, I think, this is really, I think is going to have a huge impact on the subject of high Q microcavities. These resonators we're using for these microcombs are not processed in my lab. They're not processed in John's lab. They're actually processed in a foundry, a CMOS foundry. And the tools have now been developed, and this is basically a 200 millimeter wafer that contains a lot of different kinds of waveguides, but we're zooming in on some resonators that are on board here. And you can see the kind of distribution. I think I've got it over here. So here's the wafer. This is a Q map. And you can see that most of the resonators, there were 72 tested here all over the wafer, have Qs over 200 million. There's other work, okay, where these Qs are now up, to over 400 million, and they're rising. And what this does is it means we now have a mass-produced, CMOS compatible technology that's allowing us to create, high Q resonators. And not only that, these resonators allow us to go on and make, dark solitons. And so this is a big, technological step that's going to, I think, really be useful, certainly in the microchrome subject. I just mentioned real quickly that the feedback process between the pump laser and these little cavities also line narrows, okay, the 3.5 pump dramatically, taking its short-term line width all the way down to between 1 hertz and 10 hertz. And the coherent pumping process, combined with that line narrowing, transfers that ultra-narrow line across the comb spectrum. And so this is data where we're showing that, the comb lines themselves actually are carrying all of this nice coherence. And so this is really important for WDM or coherent, transmission systems. All right, so let's look at systems and the last, part of the talk here. Okay, so not surprisingly, with all of the, success that this field has had in the last 5 or 6 years, and it's just kind of an indicator of level of interest. But 6 years ago, there were only 1 or 2 groups, okay, that could make soliton microcombs. And if you look around the world now, there are 16 groups, okay, that are actually fabricating, microcombs on, all the, Russia, Asia, Europe, okay, US, everywhere. And essentially, everybody, is having success in doing this, in different platforms, and have, different interesting ideas they're exploring. But one of the important developments has been that the tabletop application space, which was already well developed 5 years ago, kind of hinted at that, hinted at the importance of home technology for spectroscopy. I just talked about data transmission. There's a whole set, I talked about synthesis, about clocks, but there's a whole spectrum of applications out there. LiDAR, there's a special type of LiDAR called dual comb LiDAR, combines the best of time of flight and interferometry. There's a whole subject that the astronomers are very excited about called astrocombs that was introduced about 10 years ago. We found ourselves embedded in this subject, working with astronomers, transferring, microcomb technology, okay, that's being used at the Keck Observatory and at Palomar, okay, in the search for exoplanets. And so this has happened really quickly. And so the good news is that the performance of the little microcombs is, on par, okay, with the prior comb technology, the tabletop comb technology. And so it's giving us a pathway to miniaturization. One other exciting feature, though, of the little microcombs is that actually their size, their tiny size, naturally lends itself to extremely high repetition rate. Like microwave rates, K-band rates, millimeter wave rates are sort of naturally occurring in these little combs. And those are rates that are difficult to access with the larger tabletop combs because of their physical size. And these rates turn out to be very useful in these 4 applications. Okay, so K-band rates are ideal for the astronomers. They're very important in LiDAR because it involves or it enables very rapid sampling of fast-moving objects. So this was work in the Kippenberg group where they actually imaged a bullet, okay, using a couple of silicon nitride combs. Dual comb spectroscopy, very, very rapid spectral sampling is enabled. And I've already mentioned data transmission. And so here it's kind of like the WDM channel spacing is a better match. Okay, it's like a K-band, okay, millimeter wave band frequency that is easily accessed by microcombs. But the bigger news, I would say, okay, has happened over here. And there's been a tremendous amount of interest in clock technology, in synthesis technology And here there have been a couple of big programs that one of them, this one in particular, is actually just finishing tomorrow. Okay, the final deliverable on it, and I wish I had a nice picture of this. I'll show you kind of an earlier picture of it in just a moment. But this is a full synthesizer, and using microcombs. This program is run for 5 years, and you can kind of see the schematic for it. This was out of the original proposal. This was led out of Santa Barbara, so a lot of credit for this goes to John Bauer's group, who kind of really, steered the whole effort in the right direction. But again, it's doing this, and so its idea is radio to optical or microwave to optical, and synthesizing frequencies on demand. And this was actually possible. The early report on this was out just a couple of years ago. This was kind of showing the basic schematic over here. There's actually 2 microcombs that are used in this for reasons I don't have time to talk about, but here's the comb spectra. Here's the octave span. This was a silicon nitride comb right here. And the little dark band you can see in the middle, that's a microwave comb. That was one that we furnished to pay for this project. And this, like I said, this is a 2-year-old image. I really have to replace it because it's a lot fancier now. I've seen the one that's going to be presented to DARPA. But it gives you the idea of the size scale. And I have to, this has everything on board. There's the CMOS electronics, the pump lasers, the microcombs, all the controls. And it basically is a functional synthesizer. And it was tested in kind of an earlier version at NIST a few years ago. And this is data. This is out of Scott Diddham's and Scott Papp's group. They were on our team. And for this test, what they did, you might wonder, how do you do this? Because you can see this was a pretty interesting measurement. They're measuring optical frequencies, but they're doing it, at 1 to 2 hertz, okay, absolute, accuracy, precision here. And so what they did is they actually took a maser. They used the maser as the reference. And that was a microwave reference. They fed that maser into this little microcomb synthesizer, and then they took the same maser, they fed it into a tabletop synthesizer that was a fiber comb synthesizer, and they compared the fiber comb synthesizer against the microcomb synthesizer, and then you get these nice results. And here was something else they did, and there's a tremendous amount of other data that can substantiates all this. You've got to look at the paper to see it. But this one kind of gives you an idea, kind of a glimmer, okay, of what can now be done and what, the future, I'd say, of instrumentation is going to be, in 10 to 20 years, okay, maybe even sooner, we'll go to the Thor Labs, catalog, and we'll see little tiny devices that will be optical synthesizers, and you'll have this kind of capability where we will, program in this case, they were programming in little 16 hertz shifts using a graphical user interface, okay, on this synthesizer. And you have to remember, this is not relative, this is absolute. So you'll type in 14 significant figures, okay, on your synthesizer, and it will essentially emit an optical wave, okay, that is a sine wave at that frequency. So this is going to be a very, very exciting new technology to have in the laboratory. And then along with that, of course, there's been interest in the clocks. The clock technology is a little bit behind, okay, in terms of the synthesizer. This was an early clock demo using a rubidium 2-photon transition, and worked really well. Okay, the paper on that is out just a couple, 2 years ago, and actually there's now programs running where that thermal rubidium cell has actually been replaced with a cold atom clock, and so there'll be some reports out on the cold atom clock results in the next year, and those are looking real good too. All right, so that's where I want to stop and now look at kind of where does this leave us. And I'm going to have, kind of my outlook, as I indicated when I started the talk. I mean, sort of near term, long term. All right, so first of all, the one thing that, despite, the excitement I think that everyone has that is working on, microcombs in terms of its technological impact, you have to be mindful of the fact that actually there is a pre-existing technology out there, which are, the conventional frequency combs, which themselves are really—
Sorry to interrupt, Kerry. Maybe could you wrap up in maybe 1 minute?
Yeah, sure I can. Yeah, Grace. Yeah, sure. Hang on a second here. Yep. So basically, short term, okay, is that this little miniature technology is not going to replace those commercial devices, but it's going to actually, find little places, places to go, niches really, where size, weight, and power are important. And I'm showing you two here. Okay, so one, okay, probably astronomy. There's already, groups that are thinking about astrocombs in space, okay, for exoplanet research. And the other, okay, clocks in space. And it turns out this is a really natural fit because we already do that, all right, for GPS. And so this is kind of a vision of a constellation of these optical clocks. And if you put them up there, we not only can improve the GPS system, but there's actually a lot of big science that can be done, which you can kind of see in this diagram. And then the other, and then I'll finish here, the other kind of longer term picture, and this comes back to the overall theme of the talk, is that, for many, many years, all right, what we've had, many decades really, as indicated, optics and electronics have been really largely isolated. That started to change with the chains, but actually that isolation was broken, okay, 20 years ago with frequency combs. And now the interesting, question for the future is that, as we see microcomb technology provide really a coherent bidirectional link that's going to be chip scale, what's going to happen? And I think it's pretty clear that, we'll be engineering circuits in the future in a much more coherent way or a unified way, okay, where, the optical side and the electrical side will be fused together. And so this itself, I think, is going to probably launch entirely new, okay, technologies, but that's going to take a while. I think that's more of a long-term picture. And so with that, I'm going to conclude. And I just want to thank, everybody that's been involved in this work, many of the collaborators, obviously our sponsors, and then also, again, thank you for the opportunity to be here, the student chapter at the University of Toronto. And here's a couple of interesting reviews, okay, one on microcombs and the other on frequency combs in case you want to dive into this a little more deeply. So I'll stop there. Okay.
Okay, thank you. Yeah, thank you so much for the very exciting and informative talk. People are cheering on virtually with their silent applause. It's a bit philosophical. Anyway,
Right.
if we clapped, is it really a clap now? Anyway, so we would be taking questions, and Professor Vahala has time, so we can go over time. It's not a problem. So please type your questions in the chat, and I can call on you if you want to speak up. That's fine. If not, I can also ask for you. So the first question comes from Lee Chen.
Yeah. Oh, yes. Hi. Thanks very much for a really great talk, very informative and educational. I have a question about the stability. I know, for the Moloch lasers, there are two frequencies that you need to stabilize. One is the cavity length, and the other one is the group velocity, phase velocity, the dispersion. Right. How does that? How was that implemented in this microcomb?
Yeah. So, no, you've hit on really one of the tricky things, okay, in the self-referencing that was done, because, I mean, in the larger devices, it was worked out real quickly how you could have these two knobs, right, to control repetition rate and then also to control F0. So it's kind of interesting. In the microcombs, the F0, okay, is actually the easier one, because essentially what you do is you simply tune the pump laser. As you tune the pump laser, the overall comb spectrum itself moves around because the pump is one of the comb teeth. And then the repetition rate, okay, well there what you can do is you can change the refractive index, all right? So you can heat, okay, feedback to the temperature, or use a little bit of Kerr nonlinearity to actually tune it. But there's nonetheless, okay, some coupling, okay, between those two knobs. They're not completely independent. And so you have to have, some, kind of, sort of electrical, control, okay, that allows you to sort of, orthogonalize those two mechanisms. And so it was not, I wasn't involved in the early self-referencing of the tabletop devices, obviously, but that was a really tricky thing to work out, okay, in the synthesizer. It was one of the, kind of, I would say, surprise problems, okay, in the device. More recently, okay, so this is kind of a really recent development, but these devices where we feedback, okay, to the pump. And so we have this sort of what we call turnkey mode of operation. There it gets a little easier, as it turns out, because what we have is the feedback phase, okay, between the cavity and the pump laser. There's no isolation. So we can electrically tune the feedback phase by putting, for example, a phase control section on the Pre-5 chip. Mm-hmm. And that gives us fast tuning control of the laser frequency and therefore the F0. And then what you can do is you can put, power modulation, right? You can just control the return path, attenuation. And that gives us the other control knob we need, okay, to actually vary the repetition rate. So you've got sort of like two natural built-in control knobs, okay, in that sort of system. So that one looks like it's, heading in, an easier, control direction for the future. But yeah, I mean, that is a really, that was a tricky thing to work out, I would say, originally. Yeah.
That's amazing. Thank you.
Yeah.
There's another question from Kristen Coate. She wants to ask. Yes, hi.
Sure, hi. Thanks for the talk. I was just wondering what sets the shape of the comb, or like the intensity of each tooth of the comb.
Yeah, okay, so all right, so I'll give you three, okay, different versions. Okay, so start with the one that is, if you look at the microcomb literature right now, that's the one you'll see most of the time. It's a hyperbolic secant squared. And so I had those little, spectra up earlier, and they really are phenomenal. I mean, they are real. You can check them over 5-6 orders of magnitude, and you've got this beautiful hyperbolic secant squared. And that just comes about, okay, from actually having primarily second order dispersion, okay, on the mode family that's, forming the soliton. And it drops right out of the Lugiato-Lefebvre equation. So there's like perfect agreement, okay, there. Now, if I go back just a chart here, maybe I can, just do this and let me jump back right here. Okay, there is another feature, okay, that pops up. And so here, this is a hyperbolic secant squared, okay, if you can see that in the diagram. But you see these little wings over here. And these are not part of the soliton, but this is a very important trick that was developed in the last few years that we've borrowed actually from fiber optics. And this is adding higher order dispersion into the cavity. And so we'll add in third order dispersion, even fourth order dispersion. And what happens is that you can kind of bend the shape, okay, of the mode spectrum out in the wings of the soliton. And so in here, the dispersion looks second order. So you see like a parabola, but out here, the parabola turns around. And as it turns around, there's a crossing point over here where there's a pickup in energy. And this is what's, these dispersive waves, okay, are formed there. And they allow the little soliton comb to throw coherent power out into these wings. And the reason that's done is that makes the self-referencing process really, much easier. So this is another kind of feature, okay, that you'll see in the comb spectra. And then finally, I'd have to go back, maybe I can't go back far enough, but the other kind of spectrum, and you can kind of figure out what this looks like real quickly. But the dark solitons, so these are all bright solitons. The dark solitons are more like square waves. And so if you take the Fourier transform of a periodic square wave, that is what you will see, okay, in the comb spectrum. So it is a sort of a regular, kind of look to it. I had one of them up a little earlier, but those are the three, kinds of shapes, okay, that you will see in the literature. Hyperbolic secant squared with these little wings, these dispersive wave wings, and then these sort of strange, I don't know how to describe them, but they're like the square wave Fourier spectra. And so if you check the literature, that's what you'll see, and that's why they look that way, basically. So.
Awesome. Thanks so much.
Yeah.
So next, there's a question from Eric. Eric Chu? Would you like to ask your question there? Oh, no, Mike. Okay, so I will ask. So Eric is a postdoc in Toronto. So he has two questions. The first is, do you have to compensate for the dispersion of the waveguide cavities so that the repetition rate to FSR ratio remains constant?
Oh, I see. Yeah.
Is that does the dispersion have to be managed?
Yeah. No. Yeah. So it's interesting, but yeah, the answer is that we need to pay attention, okay, to dispersion. And so I mean, there's this whole little, kind of name now that you hear thrown around a lot about dispersion engineering inside the microcavity, and so you do have to worry about it. All right, but inevitably, there's always misalignment, okay, of the the natural frequencies of the resonator as a result of dispersion relative to those perfectly spaced, comb lines. And in some sense, kind of understanding, what is it that determines the spectral extent of the comb itself? It's actually that sort of misalignment, okay, that starts to occur between those, where the energy's at in the soliton comb, for example, where it needs to be as a result of, lying on a perfectly evenly spaced or equally spaced grid of frequencies, where that grid is and where the actual frequencies of the resonator are at. And so for second order, anomalous dispersion, the resonator frequencies are walking off, all right, from the soliton comb. And the further away you go from the pump, the more they're walking away. And that walk off is really what's limiting the bandwidth, all right, of the comb. And so I've got this one little picture I'm showing you right here. So here's a little soliton comb. There's a couple little hiccups in it you see here, but the overall spectral width of that, okay, the fact that these are dying down out here, it's a result of the fact that actually there's this misalignment going on because of the built-in dispersion, right? So now you know that, and what do? Well, you can reduce the second order dispersion and you try to pull back on it. And as you pull back on the second order dispersion, the comb will broaden. And so this, control of that second order dispersion, reduction of it, trying to take it as close to zero as possible, gives you one knob, that you can use to actually broaden the comb. Unfortunately, there's noise. I mean, there's noise in the dispersion. And so that little trick, has a limit. You can't, take it as far as you necessarily might want to, or as far as you think you can. But to answer your question, yeah, there's a walk-off. And the walk-off, at kind of a, hand waving level is really what, kind of is setting the spectral extent of the soliton in this case. In fact, these little wings that I mentioned down here, that are these dispersive waves, that's another way to understand what's going on there, that, you've got, again, if you can imagine the dispersion curve, it's doing this, it's a parabola right in here, and then the higher order dispersion pitches it back around. And so out here, at this point, and at this point, the soliton comb power is now becoming resonant again. It's becoming really strongly resonant, okay, with some modes that you've kind of pulled back in, all right, by introduction of this higher order dispersion. And now the comb can throw power, okay, the soliton can throw power out, okay, into these lines. Those lines are not, by the way, they're not part of the solution of the Lugiato-Lefebvre equation. They're just acting as a load, right? They're like a new loading mechanism on the soliton. So it's like you're throwing in some kind of resonant system out there that's, pulling power, okay, out of the soliton and its wings. And
Do you shape the resonator at all to
yeah, that's right.
Adjust your dispersion?
You can do, that's exactly what you can do. You can do all sorts of little interesting tricks, okay? You can shape the resonator, you can introduce, so one of the ways we do this is we have geometrical dispersion that we can, throw in. The aspect ratio, I mean, some of the really, sort of simple things that are easy to, implement in a fab, just the thickness and width of the waveguide, what is that aspect ratio? That actually controls, okay, these dispersion parameters, geometrical dispersion parameters. You can put a tilt, okay, on one of the, the facets that will, change things. You can change the width of the guide. You could introduce another resonator. There's a very recent paper just out last month from a group in Sweden. This is, the group at Chalmers, and they're basically taking two resonators. Okay, so two microcavities, letting them couple together, and then there's a set of whispering gallery resonators that actually, will couple together. And what this does is it allows them to create a local region of dispersion that enables the triggering of dark solitons. So there's a whole, kind of call them geometrical, configurational, range of games that can be played to engineer dispersion, and then use that to to modify what's going to happen with the soliton. And so kind of a fun area, okay, in its own right, in terms of the kind of physics and engineering, okay, sort of working hand in hand there.
And the second question from Eric, and it might be also illuminating for all the students in the audience, is there a difference between a ring resonator mode and a whispering gallery mode?
Yeah, yeah, okay, so depends on who you talk to. Okay, I guess in principle, all ring resonators are whispering gallery, all right? And so everything with a turn in it, all right, that involves a dielectric is a whispering gallery. Now, why is that? Well, okay, the whispering galleries, kind of the acoustical definition, goes back a century ago, and it's literally a guided mode, okay, around a hard boundary, okay. Any of the St. Paul's Cathedral, okay, is it's the whispering gallery, all right. The modern sense of whispering gallery in optics, kind of the qualifying, characteristic, at least in my way of looking at it, is that it's quasi-total internal reflection. It's not perfect total internal reflection. So perfect total internal reflection, of course, is what happens when you have a flat interface, high dielectric to low, or high index, low index. You're coming from the high index side, you get 100% reflection, okay, beyond the critical angle. You curve that interface a little bit so that you're now in the whispering gallery, and now you've got the mode that's sort of arching around. And if you look at the wave equation, what you can see is that the wave is tunneling. It actually is, it leaks. And so when we say whispering gallery in dielectric resonators, what I'm thinking about all the time is that I've got a structure that's not a perfect resonator. It's actually leaking all the time. It's leaking just a little bit of light because it's tunneling. There's a tunneling gap there. And if you make that resonator too small, or if the index contrast is too low, the tunneling rate becomes dominant, and it determines the Q factor. And so we're always designing resonators, okay, either with high enough index contrast from the core to the cladding, or we're making the radius large enough, all right, so that actually that tunnel leakage is not the dominant effect. And typically, it's easy to do. I mean, in like a silicon nitride structure, like what I've been showing you here today, in oxide or in oxide air, typically that leakage rate is going to be giving you Qs that are above 1 trillion, right? So you don't even worry about it. But you can make the structures. It's easy to fabricate, whispering gallery structures that are so small that they're completely dominated by tunnel leakage. But that, in my mind, okay, just as practitioner, that's the distinguishing characteristic of an optical whispering gallery. It's not perfect. It's always leaking a little bit because of this tunnel leakage. So yeah, it's an interesting question, and yeah.
Okay, great. Yeah, thanks for thank you for the answer, Eric says. So, so with that, since we're over time, I think it will be very good to wrap up and let us all thank Professor Vahala again for this really exciting and inspiring talk. And thank you, everybody.
Thank you.
We'll clap.
Okay, bye-bye.
Okay, thanks.
All right. So I guess Joyce, you're staying.
Yeah. I will.
Okay, and I'll join later then.
You're at 4:15, right?
Yeah, I'm at 4:15, so I'll join later.
I'll make
Okay.
sure that the call is active.
So Lee, I should just come back to this Zoom link right here around 4:15 your time.
Yeah.
Okay.
Yes.
All right. Okay. Will do.
Okay. Thank you. Bye-bye.
Okay.
See you in a little while.
Yeah.
Thanks.
Bye.
Okay. I guess maybe the one issue with using the same call is that we still have a few people hanging on here. I can remove everybody. Just give me a moment.
And also, please turn off the recording.
Oh, yes, of course.
Thank you.